In the 1840s, two men in different countries were building the idea we now call a vector. Neither knew of the other's work at the time. They arrived at it from opposite directions. One of them was William Rowan Hamilton, in Ireland, working through that decade on a system he called quaternions. He needed names for the parts of it, so he took two Latin words. One meant a carrier, a thing that transports vector. The other meant a ladder, something that only measures up and down, scalar. Those are the words you still use. They come from a piece of 19th century algebra that most students never see. The other man was Hermann Grassmann, a schoolteacher in Stettin. He published a theory of extended quantities far more general than anything Hamilton wrote, and almost nobody read it. It took decades before mathematicians recognized what was in there. Now, here's what almost everyone believes about the object those two men were circling. A vector is an arrow with a direction and a length. It sits in space and points somewhere, and that arrow is the real thing. The column of numbers is just how you write the arrow down. Bookkeeping, coordinates so you can do the sums. That's a reasonable belief. It's how the subject is usually taught, and it works for a long time. But if the arrow is the real thing, why is every single operation in this subject defined on the numbers? Start with the definition itself. A vector is either viewed as an ordered tuple of coordinates or as an arrow in a coordinate system. Take the vector v with coordinates 3 and -2. On the left, that's a pair of numbers, 3, then -2. On the right, it's an arrow from the origin, 3 units along x, 2 units down. These are not two vectors, one vector drawn twice. The notes are blunt about this. From a mathematical standpoint, it doesn't matter which way of thinking you take. So we'll always use whichever interpretation is best for understanding the problem in front of us. Most of the time, the vectors here are tuples of n real components, where n is a natural number. That makes them elements of the vector space R to the n for us. N is 2, the flat plane on your screen. There are exactly two basic operations: adding two vectors and multiplying a vector by a real number. Everything else in the first half of linear algebra is built out of those two moves. And each of them is about to be defined for you in a very particular way. Every rule you're about to learn, is it a rule about arrows or a rule about numbers? Physics is why the arrows exist. A force has a direction, and so does a velocity, and so does a displacement across a room. Push a crate north, then push it east, and it ends up northeast. You laid one push after the other. That picture was in use long before anyone wrote down a definition for it. Grassmann went the other way entirely. He started from rules, formal operations on quantities that had no picture attached to them at all, and no promise of ever getting one. That's roughly why his book sat unread for so long. There was nothing to look at. The subject you're learning arrived from both ends at once, and it kept both. Which is why its definitions are written in numbers and its intuitions are drawn as pictures. You're expected to translate constantly. Grassmann's addition rule was written for things that had no picture at all. So what happens if you run that rule on numbers, and then look at what the arrows did? Here's the rule in general. Let V have components V1 and V2, and let W have components W1 and W2, both in R2. Their sum is the vector whose first component is V1 plus W1, and whose second is V2 plus W2. That's it, add the components. Nothing about direction, nothing about length, no picture anywhere in the definition. Concretely, our V is 3 minus 2. Bring in a second vector W with components -1 and 3. 3 plus -1 is 2. -2 plus 3 is 1, so V plus W is the vector 2, 1. Now draw it. Start at the origin and walk along V to 3 minus 2. From there, walk along W. You land on 2, 1. Head to tail, and nobody put that in the definition. The arithmetic produced it. Do it in the other order. Walk along W first, then V same endpoint, so the order is arbitrary. That's the first property in the list of vector properties. Not a fact to memorize, but a fact about adding numbers seen from the side. Scalar multiplication works the same way. For any real number c, c times v is the vector c times v1, c times v2. Take c equals 2. 2v is 6, minus 4, same direction, twice as long. Now let d equal -1.5. Then d times v is minus 4.53, half again as long, pointing the opposite way. Notice there was no special case for the negative. The rule multiplied both components and the flip fell out. This is why these numbers are called scalars, they scale. The notes define minus v as minus 1 times v, the same rule again, and it's why v minus v is the zero vector. Adding 0 changes nothing. Scaling by c plus d is the same as scaling by each and adding. All of it is component arithmetic wearing a geometric coat. So here's the question the arithmetic has just made answerable. Suppose you're allowed to scale v and w by any real numbers you like and add the results. What's the set of points you can reach? Grassmann was writing for arbitrarily many components at a time when the picture ran out at 3. Nobody could draw his objects or check his reasoning against a diagram. You either followed the rules or you closed the book. Most people closed the book. Recognition came decades later, after other mathematicians had rebuilt pieces of the same thing independently. You can see what he bought in a single line of your notes. The concept generalizes the same way to vectors with n components. One sentence, short because Grassmann already paid for it. And the moment you allow every scalar at once, the question changes shape. You stop asking where a vector points. You start asking what it can reach. Those turn out to be very different questions. Here's the definition that answers it. Let w and v be two vectors. Every vector you can write as c times w plus d times v. For some scalars, c and d is a linear combination of w and v. In components, that's the vector with first entry c v1 plus dw1 and second entry c v2 plus dw2. Two dials. One scales v, one scales w. Turn them freely and collect everything you land on. That collection has a name. The set of all linear combinations of vectors v1 through vp is called the linear span, written span of those vectors. A vector u belongs to it exactly when u can be written as c1 v1 plus c2 v2, and so on for some scalars. Start with one vector. The span of our v, 3 minus 2, is every scalar multiple of it. Scale it up, scale it down, flip it, and you sweep out a line through the origin. That's all one vector gets you. Now bring in a new vector and call it u with components 1 and 2. Two dials and u points off the line. Span of u and v is the whole of R2. Every point in the plane is reachable. So two vectors span the plane, except they don't always. Take another new vector and call it z with components minus 6 and 4. Z is minus 2 times v, it's a scalar multiple, so it was already in the span of v, and v was already in the span of z. The span of v and z is just the span of v, a line. Two dials, one direction's worth of reach. And on screen, those two arrows look genuinely different. They point opposite ways along that line, so the picture says two directions. Only the numbers tell you it's minus 2 times v, only the picture makes you believe the answer is a line. Neither the arrow nor the column is the vector. They're two instruments for one object, and fluency is knowing which one to pick up.